So lead-free is, I highlight lead-free because I think the challenge of the stability is probably rather more interesting in lead-free than lead-based. But I will give a general introduction to this topic, following up the talks that we had this morning. So I think this audience now is aware of what this perovskite crystal structure is. So this slide also was shown. So I can go very quickly on this and go to what I believe are the main challenges at the moment. So stability, but I'm trying to convince through my talk that we have stable device in working conditions. So the key words are working condition. I will show device in working conditions, so they are very stable. And that's what I anticipated. What is I found very fascinating, interesting as next challenge, which can make us working for the next 10, 20 years, as I was discussing with one before, is the lead-free, so the lead toxicity. So this is done on purpose to give us some job to do for the next decades. First question is, how do we measure stability? No, this was kind of anticipated this morning. I think it's very important, still unclear. One of the first understanding about measuring stability of perovskite is that we need to measure the device under maximum power point tracking, which means the device has to be underlined and applied voltage around the maximum power point. What I'm going to show data relevant regardless the device architecture. So you can have PIN, NIP, meso, no meso, or regardless the perovskite composition, contact layer. So I try to generalize this result by observing data from different structure, different material composition. This something that we did like a few years ago was still actually here in this building working. I was back in 2016. We published this work like to kind of summarize our at the time understanding about stability. At the time there was still like the trending topic of hysteresis, and we trying to correlate, or more than correlate, like combine the concept of hysteresis to the stability, showing people that we have to really be extremely careful when we look at the stability in terms of hysteresis of the measurement of the JV. Here was the data we published at the time. So when we measure in MPP device, that's how it looks like more or less over 100 hours. And that's how the JV looks like. So the power conversion efficiency as extracted from JV was systematically overestimating the actual efficiency of the device. And the reason was the hysteresis was actually higher. So in reality, we were not measuring actual power output, but we were measuring more hysteresis. So that was the trigger that pushed us to strongly encourage towards MPP. And then when people start to look at this data, and now it's kind of established that if you want to talk about stability, you have to measure the MPP. This is something that I always like to show, but I get a lot of criticism when I show in the conference. But I think this is a very nice environment, the safe environment to show this. So what is data have? I think most in these rooms are mostly PI. I don't know how many students there are, but I see many PI. So I don't think you guys go in the lab very often, and me neither. But I collect a lot of complaints. I think you also complain from PhD because they come back with an experiment that failed, and then a second one that fails, and then suddenly an experiment works, and we eventually can extract some piece of information. So I said with my students, let's do this job. Let's put together all the data you collect to answer this question. So we were comparing like two contact materials. I mean, it doesn't matter which they are. So self-assembly, monolayer, organic molecule, nickel oxide, HTM. And these are all the devices that he made on the data distribution. So you see it's like spread all over the place. Eventually something approaching or surpassing 20% for the SEMS against the nickel oxide. But what is really interesting, that nearly 50% of the devices that they prepared failed. Failed means they were not usable at all. So they were piece of glasses to be trashed. Okay, so this is the reality of lab work. So we have to take care of this. So why I'm telling that? Because when it goes to stability, things becomes exponentially more complex in terms of variability of the result. So we have to take into account that, and we cannot rely on one MPP trace. We have to do statistical analysis. And that's why when I moved to Berlin, I started working in collaboration with industry to set up like this instrument, which is essentially we call MPPeter, because it tracks the MPP of hundreds of devices in parallel. So it's nothing else than an MPP tracker, where we can load like hundreds of devices and collect like thousands and thousands of traces on a weekly basis. So we at some point had a lot of data, and we could like start to look into like big data analysis to figure it out what was going on. And then there's the second point. So by looking at this bench of data collected over like 3 or 4 years now, so thousands and thousands of MPP traces from different devices, we arrived to a very probably trivial conclusion that the highest efficient devices are also the most stable devices. I don't know how much this was obvious to you. It was not to me. I was thinking the opposite in reality. I was thinking that if you push for efficiency, you cannot push at the same time for stability. I think a little bit when you think of Formula 1 cars, no? Like if you push for extreme performance, they will not last too long. I was thinking about the same device. I was wrong. I was totally wrong. So if you make a high efficient device, you are also like unintentionally chasing after stability. And here is the evidence of this. So these are, we divide all the data. So these are over 2,000 independent devices. 2,000 independent devices. We divided the data in 5 groups of efficiency. So they are the groups of device with an efficiency below 10, between 10 and 14, and then so on until all the device with an efficiency above 19%. And then we plot this against the losses in efficiency after 150 hours. And this is how we got. So essentially, if you go down the mean or the median, you see that which is in a linear regression. So it goes down this way. So basically, the losses moves the lower, moves towards a lower number as the efficiency goes up. So the highest efficiency is also the most stable device. This is statistically relevant. So in this 1,000 device, there is everything: NIP, PIN, inorganic, organic, triple Carai, double, whatever you like. And this is if you clean up a little bit of data. So this is essentially the same graph, but clean them up. So that's what you get. And I was very intrigued by this linear fitting, because if you look at the number, you see, if you look at the dashed line, you see that essentially the degradation goes to 0 around the Shockley quasar limit. So essentially, we're saying that if you are capable to make the perfect device, that means we're also going to make the most stable possible device. The 0 degradation condition is achieved. This is not far from what Wolfgang said this morning when we talk about open circuit voltage aging condition against short circuit voltage aging condition. We essentially said, like, if you don't take out the charges that you generate into the system, that has to go somewhere, and that goes into activating degradation mechanism. But if you keep them out, so if you go an efficiency which is 100%, or in this case 33%, then there is no energy left for degradation pathways. So this is how I conceptualize this concept. But this data, but this is all like speculation. There's no evidence. But I think I found very interesting. I don't know if I don't see you very enthusiastic, but I'm very enthusiastic about this. That's another piece of data analysis that we got from this bench of MPP traces, is that we were capable to cluster the decay curves in 4 groups. So this is a data managed by a postdoc, which is an expert in data analysis and machine learning. So I know nothing about the methods here. I only get the results. So essentially, you can let the machine analyze all the data, all the traces, and then the machine finds out that these 4 groups. So there's a groups of device which age like this. So initial rise in efficiency, and then this linear decay. The time scale is always 150 hours roughly. There's a second cluster device which shows like more or less an exponential decay, and then you always exponential, but then faster exponential. Interesting, if you again go back to the groups of efficiency, you see that the cluster 1 is indicative of device with highest efficiency and then highest stability. So somehow we can use this initial trend in MPP to predict how the device will behave on the long run in terms of stability. Essentially, the cluster 1, if the device behaves like this, so a gentle increase in efficiency and then a linear trend, that's indicative of a promising device in terms of stability on the long run. On the contrary, if we experience something like this, if we don't experience this initial gentle rise, chances higher that these devices would belong most likely to the lower efficiency, lower stability groups. And that's, of course, very clear when you have this fast initial decay, but that's, I think, it's pretty obvious. So what we are looking for is this, like gentle initial rise in efficiency and linear trend. Where we are at the moment, so we apply several different approaches, like combining perovskite formulation, new contents, passivation, whatever you like, encapsulation, and so on and so forth. And where we are now, so we have a T80 above 4,000 hours. Just to get you an idea, the silicon, it gets above 20,000 hours. So I don't know if you are optimistic, you say, oh, this is not that bad, it's only like factor of 4 or 5. If you are pessimistic, we're far off. So it's up to you how you want to read this. These are the reality. So these are the number. And that's how we get there. So that's the methods that we recently published to get this 4,000 hour T80. So we use a polymer into the perovskite precursor solution. And essentially, we managed to control the arrangement of the crystallites of the perovskite film. We moved from, let's say, a more porous system to a more compact system. But what I believe is really important here is that considering the amount of polymer that we add into the system, we managed to coat the crystallites within the perovskite film with this thin shell made of polymer, which is soft. And so when we age the device, we induce stress. I do believe that the mechanical stress that we create into the system causes degradation, and by using this polymer we prevent this mechanical stress. If you read the paper, there's nothing mentioned about mechanical stress, but that's what I understand about the system. So, but unfortunately it's very difficult to prove. So since you have to make the reviewer happy, you don't write what you believe, you write what you have evidence of. So this polymer does a lot of bunch of other things that you can read in the paper. I don't want to bother you here because they have nothing to do with the stability. So this is the result. So we have efficiency well above 24%. This is the stability under MPP. So MPP, continuous illumination. So we have like after 1,000 hours below 5% of losses. That's how I extrapolate the T80 of 4,000 hours. And the control goes down like to double or two times essentially the T80, half of the T80 that we got for the polymer treated sample. What was very interesting, that's the reason why this result became very appealing, is that we prove rather stable system against temperature variation. Now, when my postdoc proposed this to me, I said, why is temperature variation so important? I mean, a device will never experience a variation of 100 degrees, but in reality, it will experience a variation roughly 100 degrees, because when you illuminate the device, the temperature inside the device, it can easily go up to 80 degrees. So, and if outside temperature is around 0, then when you switch off the light, it goes to 0, like in a matter of minutes or even less than minutes. So getting a system which is stable under large temperature variation is important in normal standard working condition. And if you look at the state-of-the-art system, they normally behave like this. So you have like this variation with an optimum around 20 degrees. Why 20 degrees? Because we optimize the system for 20 degrees, not because there's any specific reason, because we keep on improving the system while we are in the lab, which is roughly at 20 degrees. So the system is optimized to work here. But that means that when we go to a much higher or much lower temperature, the system is not optimized and suffer in terms of efficiency and in terms of stability. When we use this polymer, the system looks rather stable. The efficiency and stability looks most independent from the temperature. That was the main achievement we got. Let's move on. Transient behavior. There was another topic that was heavily discussed this morning, and I'm highly passionate about, because actually when I was in EPF with Wolfgang, we were probably about the first to look into these topics and the first to tell people, look, we have to take care of this, especially when we study stability and hysteresis, of course, but the stability is also very, very important, because these transient phenomena or non-equilibrium condition, they have time scales of hours. So that means these time scales are compatible with the real working condition. So we cannot ignore them when we enroll the device outdoor. And that means that we need light-dark cycling to mimic the outdoor conditions. So that was something that I'm trying to push now. So we said like about 10 years ago that we need MPP tracking to look at the stability, I'm telling now that in addition to MPP tracking, we need to cycle the light. So it's not okay to use just 100 hours, 1000 hours under continuous illumination. We have to alternate illumination in dark condition on windows of hours or minutes, depending on the testing temperature. Of course, you can try to accelerate the cycle by increasing the temperature, but you have to cycle the system in dark and light. This was, again, what we published at the time when I was here in AMI. So this MPP trace over 100 hours show like a decrease or an increase depending on the architecture, depending on the content and many other stuff, but we always observe a recovery in dark. So after letting the device resting in dark for a while, there was some recovery of the initial efficiency, either an increase or decrease, depending on the initial was a rise or loss. So this was an indication that these transients were absolutely not permanent, but something which can be recovered at least partially. And what was important to notice that if you look at the time scale, so a normal daylight condition is like, let's say 10 hours of illumination, you are always here, you never reach this region. So this region is totally not relevant for assessing stability. So you have to keep the device in this transient and run it in this transient condition to understand how it will behave on the long run. So how we do that? So we, of course, we have our outdoor test. This is in Berlin. So weather is not always nice, like in Colombia, I guess. But we can do something. Temperature is a bit lower. So, but we have information, we have data. So we're starting comparing that with the accelerated indoor condition. So the idea is like trying to establish and accelerate indoor testing condition, which mimics the outdoor performance of the long run. That seems like an obvious thing to do, but I will show you. So I mean, what we do, of course, we translate the day-night cycling in this wave function. So light on, light off. That's very, I mean, simple. And that's the result, a disaster. So these are 4 different devices, and some of them tested in the day-night cycling, so it's cycled illumination, some of them in continuous illumination. So you see that sometimes the cycled illumination is like more stable condition than MPP. Sometimes they overlap. Sometimes it's the opposite, a mess. So there's no a clear trend. So depending on the device, depending the perovskite composition, the contacts, and the device architecture, you might like overestimate or underestimate the MPP trace when you go outdoor. That's a real complication because it makes very difficult to establish a standard protocol. So essentially, each device should have its own protocol for accelerating indoor aging testing. I don't have the solution, so you don't. It's no suspense to give. I don't have the solution, so that's the reality. This is sorry, it was not intentional. It's like I create too much suspense, and then so I feel the pressure of telling it. But this is the result that with the best result we get. So this is a cycle. Why I said before we don't. I think devices are stable. Perovskite is super stable because this. Because when this particle, there's nothing magic with this device. This is one of the standard devices that we are using with all the tricks that we learn from literature, from our own publication about making more stable. So this is a cycle, and this is an average of 11 independent devices cycled under one sun, 12 hours illumination, 12 hours of dark, no UV filter, so one sun, complete one sun, temperature 25 degrees. And this is how it looks like. Now the experiment is still running. So we passed 3,000 hours, and that's how it looks like. It's perfectly flat, almost perfectly flat. So I would say like the T80 here is like infinite at the moment. So that's why I believe that we don't have an intrinsic fundamental problem with the stability. The perovskite can be stable. Of course, having a stable technology is not the same than having a stable lab sample. That's a different story, but I don't see any problem there. Yeah. With me. But then you cannot publish by yourself without me. Okay, I go to my, I mean, I like this topic, so now that's what I like. Not that I don't like stability, but this is I'm very passionate about. So why lead-free? I always like to start with the motivation. So why stability is obvious, but why lead-free is not obvious? Because when I go around conferences, I always get the same question like, oh, but lead is not a problem. Lead can be managed, can be like, quenched. I mean, there's different approaches. And I always show this first slide. So lead is a problem. It has been a problem so far in many applications. Doesn't mean there's going to be a problem in perovskite, but that's been a problem in paints, gasoline, electronics, and bullets. Okay, so there's been systematically banned in this application. You can find details in this paper. So my question is like, why you expect is not going to be a problem in the perovskite? I don't get answer usually. So we went a little bit further. So we're trying to understand how people have been tackling lead in other technologies. So which implies a little bit of like expertise, which is not within my area of expertise, but also trying to pass the information that I learned from my colleagues in medicine and in agricultural land and stuff like this, environmental science. So there's a scale that I reported here, which where I plot the lead weekly intake. So we all eat some lead on a daily basis from different sources. Can be water, vegetables, plants, animals, whatever. And this intake at the moment, in average, is around here. So we have an intake in the range of 10 to the minus 4, 10 to the minus 5 gram per week per person. It's too much, it's too little. People used to say, okay, but this is kind of natural level of lead intake. This is not natural. This was natural like 3,000, 5,000 years ago. So when humans start to exist, that was the level of lead exposure that we had. Then because human activity, we start to rise our lead intake level, and we arrived in the 1980 to a peak of lead intake, not because food or water, but because atmosphere, because lead gasoline was loaded, the gasoline was loaded with lead, so with the lead was spread in the atmosphere, we were breathing lead. So that's why lead was banned by gasoline. And since then it was banned by gasoline, we start to get better and better. So this is where we expect to be in 2050, not yet back to 2,000-3,000 years ago, 2,000 years ago, but we're doing good. The question is how the perovskite era, because there will be a perovskite era, I'm sure, how the perovskite era will impact this trend. If it's perovskite applications, not only PV, capable to kind of influence this tendency. That's the key question that we have to answer. And there is no doubt that being here is not safe, because there's evidence of intellectual deficit for this level of lead exposure. So we are all have an intellectual deficit. And there's evidence of DNA methylation. So it means cancer can derive from this level of lead exposure. Of course, if you go into microgram level, you have immediate toxicity, but that's I mean, nothing relevant here. So what is relevant is that we have this chronic exposure to lead, which will end up in some long run problems that we are very difficult to correlate to lead, because we don't have like the effect and the cause of this effect are not very easy to correlate at the moment. So as I mentioned, I'm very passionate about this topic, and on my Twitter account you can find some interesting like video or papers about this. So this one I was mentioning, we all have a low IQ index because lead exposure. Or there is another, it's a very interesting one. It's a documentary about the story of lead in gasoline. It's very fascinating because it tells you how interest is controlling pretty much everything, even when those goes to human health. And this is another curiosity, like a famous painter from the past, they might have been experienced lead poisoning because they used to lick the brushes before painting. So they were like ingesting direct lead from paints. So as I mentioned, that my colleagues from Fuji University Agriculture, so they measure the applicability of lead. That's another concept we have to take into account. I learned from my colleagues. So when we talk about toxicity, it doesn't exist the toxicity of lead per se. It exists the toxicity of the specific chemicals containing lead. So if you change the chemical, the toxicity may be completely different, for the simple reason that that chemical might not access the human body so easily. And the most easiest way to access human body is like water. So water solubility is the key parameter to control. And unfortunately, lead perovskite is relatively water soluble, so it can access plants. So if you drop lead perovskite into the soil, it goes straight into the plants, 100%. If you drop other source of lead into the soil, they exist. So if you collect some soil out there, even in Switzerland, you end up finding around 35 ppm of lead in that soil, but that lead is not bioavailable, means that plant cannot collect their lead from the soil. But if you drop perovskite, they can. The question is how much lead from perovskite we need to put into the soil to make the soil dangerous. And here things becomes even more complicated, because when I talked to experts, they told me like, okay, now you have to consider two parameters. First, how much, where is the risk of dispersing perovskite into the soil? So you have to end up with the fraction of the total world production of perovskite that ends up into the soil. This fraction is here. And then you have to also understand which is the fraction of the world population which is exposed to lead contamination. And then we end up with this graph here. The safe area is here. So to be safe, we have to make sure that in a future scenario where perovskite is heavily used, only a fraction in the range of part per billion of perovskite gets dropped into the environment. That's very tiny. Okay, so which is the solution? 5 minutes to give you a solution to the problem. So the solution I'm proposing, not only me, as many people are proposing, is replacing lead with tin. And don't ask me the question that why tin is safe and lead is not. Tin is safe because it's not water soluble, as I just mentioned. Tin was actually proposed since the beginning of the perovskite in PV. So we published the first paper when I was in Oxford in 2014, and then it was kind of abandoned. The reason is very simple, because it was very difficult to manage tin in ambient conditions. So you need extremely pure inert atmosphere to avoid the tin oxidation. But things are progressing. So this is lead we are at the moment with tandem and with the single junction. With tin, we have a certified efficiency around 15%. So not too bad, I would say. So this is what we did. So it was a paper from back 2021. So we managed to make around 10% device with a stability, which was not that interesting. But the reason was, as I mentioned, the tin oxidation. So tin, different from lead, it prefers to stay in the 4+ oxidation state, which makes him unsuitable for 3D perovskite. So you need a 2+ metal in the middle of the crystal structure of perovskite. And when you make tin perovskite film, you always end up with a certain amount of tin 4, which essentially is like destroy your materials, like a source of defects, which here, if 10–20% of your material is tin 4, I would not call it defects. I would call it like 2 phases. And that's the amount of this tin 4 increase with time. So it means there's something actively producing tin 4 during the device operation. So we studied this in the detail, and we understood that actually one of the solvents, the DMSO, which is fundamental in processing perovskite, is causing this oxidation, not only during the processing, but also afterwards, because there's always some residual molecule DMSO left in the film because it's such a high boiling point. So you always ended up with some residual DMSO which cause oxidation in the device during the normal working conditions. So our goal was, okay, let's find an alternative to DMSO. I went to myself, okay, that's good. We know the problem, and I always say, if we know the problem, we have the solution. And so, okay, let's replace DMSO. That was a disaster. Because DMSO is such an important solvent for the processing of the perovskite, and we understood this only when we tried to replace it. So we had to find a solvent which, okay, solubilizes the precursors and does not oxidize a thing, but also that controls the crystallization of the material similarly to what the DMSO does, or eventually even better. So we ended up screening hundreds of solvents, and we select this 15, which somehow mimic the DMSO, the interaction of DMSO with tin. And by blending them and combining with some others, we eventually ended up finding a right combination which allows to essentially create the same binding condition of DMSO. And we managed to make DMSO-free system. Its efficiency is now about 8%. So not yet like a state-of-the-art, but we have a DMSO-free system. What is really interesting, I'm going to conclude my talk, is this. Remember all the transient behavior that we discussed about perovskite? We don't see them in a thin perovskite. This was shocking when they showed me the first time this graph. This is not published yet. Essentially, this is a typical lead perovskite, not the best, but I mean, it's a standard one. And we always have this transient behavior. So this is a day-night cycling sort of, so 4 hours illumination, 4 hours of dark. We have this transient, the device comes back, and then again, and then again, and then again. That's usual stuff. With thin, you don't see that. It's flat. You start to see some transient activity only if you heavily degrade the device. So this is an 85-year-old device, and you start to see some weird stuff, let's say some transient, I would call. But in freshly made or nicely stored device, like there's nothing. It's perfectly flat. I think this is very indicative of the fact that there's something super interesting about tin. And probably it's also in tin, not only the solution for toxicity, but probably also the solution for the stability. Someone was asking this morning, how can we get rid of this transient? I don't think we can get rid of transient in lead for very fundamental reasons that have been highlighted by Filippo De Angelis and Maria Petrozza, published very clear mechanism why we always have this transient phenomena in lead. And we are working with them to try to figure out why we don't have this mechanism in the tin. And so this is something that, I mean, probably it gives us job for the next 10 to 80 years.